Okay. Welcome, everybody, to our November Ask a Physicist. This will be the last one of this semester, but we will start again next semester, which would be January 30th. So look out for email, social media announcements mid-January to register for that. And just as a reminder, if you have any questions during this webinar, go ahead and use the Q&A feature at the bottom of the screen. You can ask at any point during the presentation, but we will get to questions at the end. And I think that's all I have. So I will go ahead and turn it over to the moderator for the evening, which is the Beyond Center Deputy Director, Sara Walker.
Hi, everyone. Welcome. Thanks for joining us this evening. We're really delighted to have Gerard Milburn here this evening, who's an expert on quantum systems and quantum measurement, quantum control, but is going to tell us all about time, what it is, how we measure it, how we should think about it. And I always learn something new about how to think about things when I hear Gerard give presentations. So I'm very excited about it. We'll have an open question session after, as we usually do. So please, during the presentation, if you have any questions, feel free to put them in ahead of time, and we'll go through them at the end, or you can ask them afterwards if they come to mind. Paul, I'm joined here also by Paul Davies, who is the director of the Beyond Center for Fundamental Concepts in Science, who also has thought a lot about time and might join in with the discussion period after. All right, Gerard, I'm going to pass it over to you. Thank you so much for joining us tonight. I'm very excited about this.
Thank you, Sarah. So let me just share my screen. Let me double check that everyone can see that.
Looks good.
Okay, I'll try to go to full screen mode, make sure that works. Okay.
I don't see it full screen yet. I still see like the PDF menu on the side. I don't know.
Okay. Okay, let me just stick with the PDF menu on the side.
That's fine. Yeah.
That will be fine. Okay, so thank you very much for the introduction. Yes, I'm going to talk about time, which is, of course, a very old question, an old conceptual puzzle, and also simultaneously one of the most personal ones that we face, because we are creatures that live in time. So what is time? Well, it's virtually impossible to answer in any coherent way, but a simplest approach would be simply to say time is what clocks measure, or perhaps I should pose that as a question. Is time what clocks measure? Up until the beginning of the scientific revolution with Galileo, time was governed by celestial motion, periodic repeating events like the solstice or the equinox, phases of the moon. The scientific revolution was ushered in by Galileo, who used a very simple kind of irreversible clock based on dripping water. In fact, those kinds of clocks have been used since Roman times. Oscillations of a pendulum in the 17th century, 18th century developed a high degree of sophistication. And quartz clocks came along in the middle of the last century, and of course, atomic clocks now provide our standards. So these are all very different kinds of clocks, but they're supposed to measure time. On the other hand, we can easily find pictures like this. This is a fossil of Kennewick Man, and it's said to be 9,000 years old. But the question is, Kennewick Man wasn't buried with a watch, so how do we know it's 9,000 years old? And the answer is radiocarbon decay, which is a very strange kind of clock. Radioactive carbon-14 just decays, and that's it. So it's very much like a clock with no tock. It just ticks. But that's good enough for estimating time. What about this one? Cosmological time. We often say the universe is 13.7 odd billion years old, but where is the clock that tells us that? So clearly, if clocks are what, if time is what clocks measures, that's a pretty complicated statement to unpack. But of course, we know time was not invented along with clocks, no matter how primitive they were. We've all experienced time as living creatures, and we experience it. And this leads us to the concept of what's often called manifest time, where it's time that we feel, that we experience. So it's characterized by the fact that the present always feels special. Time appears to flow, and the past is fundamentally different from the future. So what has this got to do with the time that clocks measure? And that's mainly the content of my talk. So is manifest time what clocks measure? Now, let me talk a little bit about manifest time and physical time. As I said, the scientific revolution was ushered in by both Galileo doing experiments based on simple clocks, but more importantly, by Newton making very strong assumptions about the nature of time. And in fact, there's this very famous book which gives you a brief history of time, at least from the point of view of physicists. We have Newton's equations, special and general relativity, Schrodinger's equation in quantum physics, and all these equations are completely reversible in time. If you know the initial conditions, you can predict the future, but you can also retrodict the past. And so in some sense, in those theories, future and past are the same. There appears to be no fundamental distinction. So that doesn't appear to be like manifest time or time as we experience it. And people have noticed this, of course. Here's a quote from a science article 7 or 8 years ago. The physical equations make sense, but they don't satisfy those who ask why we perceive a now, or why time seems to flow the way it does. Or Tallis, in his book on time and limitations, says physics has little or nothing to say about much that truly matters about time, by which he means matters for us. So is manifest time then in fact different from physical time? Is it something entirely different? Okay, so let's dig down a little bit closer and examine what we mean by clocks and physical time. Well, the point of a clock is that it measures coincidences between local events here, locally, and now, in the present. And to fully specify that, we have to say what the local conditions are, which ultimately would resolve themselves into forces acting, gravitational fields, but more particularly to temperature of the local environment. And that turns up in general relativity in something called the Tolman relations. So what do I mean by clocks measure coincidences? Well, the key understanding is a clock record is a count. In fact, it doesn't necessarily have units unless we choose a parametric representation. So a clock is a count. So here's one simple way to think of it. Let me see if I can get this to run properly. So this is a video, and you're going to hear a rather low resolution sound together with a clock that's ticking. And what I want you to do is to note the reading on the clock that's coincident with the sound. So this is a simple count, no units, and it just goes on and on. So when I say coincidence, I just mean what is the count when the event bong sounds. So that's what I mean by a coincidence. So let me see if I can get out of this now. Back to my talk.
I didn't actually see the clock, but I did hear.
Oh, okay. Well, let me just describe it to you. Imagine that instead of a sound, it's a flash of light, and you're in a room with a simple counter going 1, 2, 3, 4, 5, 6, 7. And every time you see a flash of light, you look at the counter and check to see what the number is. And so you can record that data this way. I'll record a 1 if there's a flash of light when the clock counts 1, and 0 if there's no flash of light when the clock counts 2. So this is what I mean event count coincidences. There's a physical event and a nearby clock. They don't interact. They just happen to be roughly in the same place. And you just simply count. And you could represent that by this function. That's a function of the clock count, n, and it's a binary valued function. So this is all we necessarily mean by local time coordinating coincidences. It's often said that in this sense, physical time is relational. It's a relation between two local physical events, in this case, a clock counter and some other event, a sound or a flash of light. Physicists typically write this in a parametric form by introducing something called little t, which is a real number, while this is a binary valued function of an integer. There are some simple theorems that show you can always parameterize it in terms of a real parameter. And that's generally what appears in the equations of physics, Schrodinger's equation, Newton's equation, and so on. But that parameter t really has no physical significance whatsoever. It's a convenient mathematical representation of these coincidences. And in general relativity, that becomes very, very evident that the parameterization invariance of general relativity has significant physical consequences. Okay, so now let's dig down to a bit more about the physics of clocks, and I'm going to put this in terms of the thermodynamics of clocks. So let me just state it as boldly as we can. All clocks, classical or quantum, are irreversible physical systems pushed away from thermal equilibrium. Now, this already is a little bit controversial because the Newtonian description of the world tended to be captured by the idea of a clockwork universe, entirely predictable. No irreversibility, it can run forward in time, it can run backwards in time, no uncertainty whatsoever. But physical clocks are not like that. They are systems pushed away from thermal equilibrium, and that's quantified by their change in free energy, which we can change by either doing work and increasing their internal energy, delta E, or by making measurements upon them and decreasing their entropy. And I wrote a review of this a few years ago now, if anyone's interested in pursuing the details. So let's look at a very simple clock, a pendulum clock, to see how these ideas play out. The important point to realize is while the pendulum may be a linear oscillator, or at least for small deviations from the vertical, it's a linear oscillator, the entire device is most certainly not linear because of the mechanism which drives it, which is this anchor wheel at the top, which periodically kicks it. And that's what you hear as the tick-tock in a pendulum clock. And the work done is by a falling mass. So these are driven by gravitational work done on the clock. The entire thing together makes up a nonlinear oscillator, which will move on to what's called a non-equilibrium steady state, known as a limit cycle, which is a stable one-dimensional attractor. And these are dissipative structures. They can only form in systems with friction. And so the work done by the falling mass is dissipated as friction in the clock, and the limit cycle forms when the work done on the cycle, one period of the clock, matches exactly the energy dissipated in the clock. So we usually describe the state of the pendulum in physics by its angular deviation from the vertical and its angular momentum, or its velocity. The escape mechanism, these kicks, only happen at particular extremes of oscillation of the pendulum. So they depend on both the angular displacement and the angular velocity of the pendulum, and that makes it nonlinear. And as I said, in these systems, they can form a stable oscillation, sometimes called a relaxation oscillation, and that is what constitutes the clock. Whoops, no, I don't want to do that, go away. So the noise that necessarily follows friction, however, complicates life. So because with friction comes heat, random fluctuations and disturbances, the pendulum, while it always relaxes back onto the limit cycle if it's given a little disturbance from some heat, it nonetheless means that the period will fluctuate a little bit from one cycle to the next. So as soon as you have dissipation, you necessarily have noise, and that means the period of the clock will fluctuate. So we need to understand how we can make good clocks in the presence of fluctuations like that. Anyway, here I simulated some equations, and here we are in the long time limit, where I plotted the angular velocity of the clock. You can see it's a nice sinusoidal oscillation. And simultaneously, I plotted the kicks, which happen twice every period. The kick is a fixed size, positive or negative, and it's clearly oscillating nicely. What does it look like for the limit cycle? Well, here I plotted it in a parametric representation with the displacement from the vertical and the velocity. And you can see if I start at the origin, it spirals out onto this limit cycle and stays there. You can see there are two kicks per cycle. There's one there and one there. Or if I start outside the limit cycle, it spirals on. So the point is this is an attractor, and that's what makes limit cycles important for building clocks. They're stable against fluctuations, but the fluctuations are inevitable because limit cycles are dissipative. So when you include these thermal fluctuations, they're sometimes called Langevin forces. Here I just plot the sign of the oscillation. It's sinusoidal, so it oscillates between positive and negative displacements or positive and negative velocities. And here I plotted a couple of them, and you can see the phase is getting disordered. It's not keeping exactly the same period. And that's because the phase diffusion on the limit cycle determines how long it takes to the clock to go through exactly 360 degrees or exactly one cycle. Sometimes it gets there a little bit early, and sometimes it gets there a little bit late. So the fact that this is a dissipative structure means the period is necessarily random to some extent. And that's what I've stated here. So in order to estimate the period, you need to ask a sort of inverse diffusion question where you say, how long does it take to move through 2 pi, to go through exactly one oscillation of the cosine function, one oscillation of the clock from one tick-tock back to the next tick. And it turns out this is given by a universal formula called the inverse Gaussian distribution or Weyl distribution. Let's not worry about the details. The point is the mean of that is determined by the frequency of the pendulum, if you don't push it too hard. But the amount of noise, the uncertainty, gets smaller as you make the limit cycle bigger. And this is why limit cycles are very good for clocks, is because if you drive it really hard and make the limit cycle big, dissipates lots of energy, but the phase diffusion rate gets smaller and the uncertainty in the period goes inversely. Sigma here is a measure of the thermal fluctuations in the system. So the important idea here is the larger the limit cycle, the more regular the clock signal. And of course, the larger the limit cycle, the more dissipation there is, because you have to drive it harder to form a limit cycle that has to be matched by dissipation of energy. And so these sorts of clocks are necessarily dissipative. And this has been something that's been discovered and explored in recent years by Urker and collaborators and lots of others, showing that the whole point of building a clock is organizing irreversibility in a special way such that the period becomes regular the harder you drive it. So here's a picture where I've shown where you drive it harder and harder and harder, and the distribution of periods gets closer and closer, in this case to 2 pi, because I've fixed the frequency equal to 1. So the lesson there is that these sorts of clocks, the clocks which we're very familiar with, are necessarily dissipative and necessarily noisy, and they function perfectly well by simply counting coincidences over a period. Now let's look at some of the consequences of what that might be. Imagine now we have someone sounding out a particular note on the keyboard with a number of clocks nearby. Say we call an ensemble of local clocks near this changing event. Now let's suppose each of these is a pendulum clock. Because each is subject to random fluctuations, random kicks, because they're dissipative systems, they won't all have the same period. Even if we start them off at exactly the same time, the period of each one, the time it takes to go from one tick to the next tock, will fluctuate. And that means if you were to count coincidences of the sound of the pianist and the clock, they won't all register exactly the same record of clock counts for a given event. We can picture that as follows. If we pre-select so that all the clocks are set at one count on the very first event, then as we count, as the changes occur in the local environment, the sounds go on the piano are being recorded, and we count different readings on the different clocks, we see they become increasingly disordered as the count goes on. And this is just a simple restatement of the fact that the entropy increases into the future based on this pre-selected event. The disorder is getting bigger in the future. We can do the exact opposite if we like. We can look at all the histories of those clocks that just happen to show the same record n equals 1 at a particular point in the coincidence record. And we can see straight away that they're disordered into the past. Obviously, there are many more records that don't happen to be post-selected with n equals 1. But if we post-select on that event at n equals 1, then into the past, the entropy appears to increase as well. The disorder increases into the past. And this is well known. Boltzmann noticed this, and Hans Reichenbach made a great deal of this in his little book on the direction of time. So this is what it looks like if we're in some local environment and we pre-select and post-select, it appears that entropy increases into the future and into the past.
May I interrupt for just a minute? I'm sorry. We have a question that came in, but it's such a critically important one for understanding what's going on that I thought I would interrupt, which is an understanding of what entropy is. So someone in the audience would just like a clarification about entropy.
Here I'm using entropy as the same as disorder. So it's the mere fact that these records start off the same and become increasingly disordered as time goes on. So they're being spread out. The probability of a count being, say, 4 for the fourth event here it's 4 for some and it's 5 for others, it's 3 for some. So entropy just refers to the increasingly disordered nature of the different counts on the different clocks. So what it means is the more events on the piano that happen, you look at the clocks and they're getting increasingly out of sync with each other due to the noise and uncertainty intrinsic to their nature. That's what I mean by entropy in this case.
Great.
I hope that's clear.
Yeah. Hopefully that clarifies. But I think probably if one person was asking more.
Entropy is a contentious issue in philosophy of physics and indeed in physics. So we'll come back to that, I'm sure.
Yeah,
But
excellent.
now let me be even more contentious. Does this mean that manifest time is different from physical time? Because now we see that there is a difference between the future and now, and the past and now, and there's no sense of reversibility at all. So if time is what clocks measure, and clocks are subject to these constraints I've just explained, then in some sense they are consistent with our understanding of manifest time. Let's do something else. There's something called the past hypothesis in cosmology and fundamental physics, which postulates that the universe started in a low entropy state. Well, from this point of view, obviously it did, because the Big Bang is the only point in the history of the universe at which all events were local and coincidences. They all happened at the same place in the same time. And so it had no choice but to become more disordered as time went on, if there are clocks around that one can use. Of course, this doesn't really answer the important question, and that is, what is the rate of disorder? How fast does it increase? How does it depend upon the cosmology of the Big Bang? So there are still many important questions, in fact, the most important questions that need to be answered about the interaction of gravity and the electromagnetic field at the early stage of the universe. But in some sense, it's not too surprising that you would expect something like the past hypothesis from this point of view. Now, what about other sorts of clocks? I spoke briefly about radiocarbon dating. Well, it turns out you can build a perfectly good clock out of a purely random system. So here we just have a two-level system interacting with a thermal bath. Occasionally it goes from the ground state to the excited state, and occasionally it decays back to the ground state. In the case of a radiocarbon clock, they all start out in the excited state and just decay. And gradually you just get fewer and fewer of them. So you just count how many have decayed. But we can always adjust it so that instead of just having a tick, we also have a tock. So it can be pushed backwards and forwards by absorbing thermal energy from the environment. And this is a pretty good clock. It turns out if we make accurate measurements of the energy, thereby reducing the entropy of the system, that is, you know with certainty what state it's in, or close to certainty. If I measure the energy continuously, I can tell whether it's in the ground state or the excited state. Then I can just keep a record of the transitions. And if I look at what it appears like, it'll be just sort of this random telegraph process where it's in the ground state, and it jumps to the excited state, and then back to the ground state. And my count is pretty disordered, but it functions pretty well as a good clock. And this is called a thermal clock. They've been around since, well, they've been around since time immemorial in some sense. But Maulik made a big deal of thermal clocks in the 19th century. He seemed to be intrigued by the fact that a thermal clock was consistent with the increase of disorder in the universe. And Arthur Eddington, a famous British physicist, also made much of this in his writings on philosophy of physics. In the high temperature limit, where the temperature of the clock is much greater than how much quantum energy you need to excite the thing, the transition rates become roughly the same. And so you can easily estimate time by just counting transitions. You can put it in seconds by putting in some rate constant. And now we see an interesting feature, and that is the estimated time depends on the estimated temperature of the environment. So we see if you have a good thermometer, you can build a good clock. But if you have a good clock, you can build a good thermometer. So in some sense, time and temperature are the jewel of each other in this picture. In fact, if you multiply the time estimated by the temperature estimated, you find for a given atom, it's a universal constant in this picture. And if you look at the uncertainties, you see they're related by this funny relationship. That is, the fractional variation in the time estimated is related to the fractional variation in the temperature estimated. And this is exactly what turns up in the Tolman relations in general relativity. And I've been wondering for some time, so to speak, whether this is a characteristic feature of any system in which time is relational in a thermodynamic sense. This brings me to my final point, which is the Ravelli thermal time hypothesis. There is a fundamental problem in general relativity in figuring out what should be the time variable. Taking this purely relational sense, you have to find some other physical quantity That's changing in order to look at coincidences with the relevant physical quantity that you're investigating. And Rovelli, a long time ago now, pointed out that any system in local thermodynamic equilibrium can function as a clock. If you can, this is a bit technical, but basically you just estimate the probability for finding it in a particular energy eigenstate. This was worked out by Gibbs and Boltzmann a long time ago. And once you know that, you can calculate what the energy of the system is, purely mathematically speaking, and you can define a flow. So this was a very abstract theoretical way of saying that if you have a system in thermal equilibrium, you should be able to back out a local time. But what I've just described is precisely that for thermal clocks. I won't go into this in too much detail, but you can set up little games where you have two systems in global thermodynamic equilibrium. Each, though, they don't share a global standard for time, and they don't share a global standard for temperature. But nonetheless, they can establish that they share a global thermal equilibrium environment just by acting as thermal clocks. They agree that 1 unit of local thermal time corresponds to n transitions in their local thermal clock. That's an integer. It's dimensionless, doesn't depend on their standards for time or temperature. And then they need to communicate with each other. A waits for n transitions on her local thermal clock and sends a signal to B. B, as soon as they get that, sends a signal back to A on what their local count measured. And then in the meantime, of course, A has recorded another number of transitions, a number of excitations between the ground and excited state. And then you can show that if they are in thermal equilibrium, the ratio of these two numbers that A gets will be approximately 1 plus or minus some small uncertainty that depends on how big n is. And of course, B can play the same game. So by using thermal clocks, they can establish that they are in global thermodynamic equilibrium with a common bath, as long as they use the same atom, of course. Okay, so, and this of course is ultimately related to this duality between time and temperature in these sorts of thermal clocks. And with that, I'll finish and open up to questions. More questions. Thank you.
Excellent. Thank you. That was fantastic. I'm sure it raises a lot of questions. So for our audience out there, and particularly for those of you that may be new to Ask a Physicist, this is a great opportunity to ask any kind of question you have about the topic of today from an expert. And so Gerard has given us some very provocative leading statements about how he's thinking about time and new ways of formalizing things. So we're really excited about having some discussion and questions, but you can bring them in on other topics that you've thought about the physics of time to get some ideas. So we had a couple questions that came in by email. So I'm going to start with those while people are thinking about formalizing any questions that they have for you. So this one comes in from Dennis Boyle, and he asks, is Minkowski spacetime, the so-called block universe, a more accurate and complete depiction of time and space than the classical pre-relativistic Newtonian depiction, despite Minkowski spacetime's omission of the idea of the present moment, the now, and the ideas of change and becoming?
Well, that's a very good question. And of course, the block universe is predicated on the fact that in Minkowski formulation of general relativity, space and time are locked together in this single geometric structure called space-time. But all of that is predicated on the assumption that we're using this parametric time, and the equations are completely reversible into the future and into the past. And so as long as you stay within that framework, you have no access to manifest time at all. The block universe appears to exist just like the universe just is. It has no dynamics. It just is. But for a local agent in that universe with nothing but local clocks to understand what's going on, the block universe doesn't have a great deal of cogency. So while it is a perfectly valid way to think about special relativity and Minkowski space, from the point of view of local agents, there's a perspective which is unavoidable. And that perspective is based on local clocks, which ultimately are clocks in our head, chemical clocks.
Great. So a question coming in from one of our audience members, Jason Pratt, is, do you think that the continuous advancement of quantum computing might lead to a better understanding of time?
Excellent question. Well, certainly it's going to lead to better clocks, because In our current way of doing quantum computing, we imagine turning on and off little quantum logic gates, and these have to be timed precisely. So there has to be some global clock which is turning on and off interactions extremely precisely. If you overshoot or undershoot the time at which these interactions are turned on and off, then the computation begins to acquire errors. And sometimes instead of doing a NOT gate, you do something which is a little bit more than a NOT gate, and so on. Now, in principle, this can be corrected away with error correction, but that has huge overheads in terms of entropy production itself, because what you're trying to do in error correction is to drain the entropy out of the system that's being introduced by fluctuations in the timing of the gates. So to make good quantum computers, you really do have to have incredibly good clocks. And in fact, in our center, our ion trap lab in Sydney, the current limit to the fidelity of single and 2 qubit operations is the quality of the clocks. And in fact, the qubits are better clocks than the clocks they're using to turn interactions on and off. So much of quantum computing is certainly going to drive quantum technology forward with respect to clock technology. The more serious question is, will it lead us to a better understanding of time? Possibly. I don't know. Currently, one of the best clocks out there is a quantum logic clock at in NIST in the United States. So very likely it will.
This is actually a great segue to our next question from Fletcher Griffin, which is, can a clock ever be 100% accurate?
No. If, as I've said, clocks are irreversible devices and some subject to fluctuations, they can't be 100% accurate. If you're prepared to pay a bigger and bigger thermodynamic cost, you can get them better and better. However, there's another limit, which I haven't even talked about, which other people have speculated on. If you have to drive it harder and harder and harder, you need to localize more and more energy in the system. And eventually, general relativity tells us you'll create a black hole, at which point the clock disappears from the discussion entirely, and you're just left with Hawking radiation. I haven't discussed that at all, but many people have speculated that that is a true quantum limit to clocks. In other words, it's the back action of the clock on the gravitational field which ultimately will limit our ability to measure time.
Excellent. So this question comes in from Lily Robinthal. Does manifest time only have a meaning in the context of consciousness? In the absence of any conscious observer experiencing the passage of time, is only physical time relevant?
Okay, so this is a very good question. First of all, it is true for conscious observers, but the trouble is consciousness is a very difficult thing to get a handle on. I would say that any learning machine necessarily needs a local clock because it has to somehow or other timestamp what it's doing to the world and what the world is doing to it in order to learn. There needs to be a sequence of steps whereby it learns from experience. And the very notion of causal structure, which sort of disappears in the traditional view of physics, where everything is reversible, comes back in when you're talking about learning agents, because they intervene on the world, they act on the world, and the world acts back. And depending on their history of interactions with the world, they can learn to compress their experience into simple physical representations. In an artificial neural net, these would be the weights in the device. In a physical neural net, they'd be physical bias forces in the device. So I'd say that any learning agent will necessarily share a notion of manifest time, with the future being different from the past and the present being special. Now, even in physics, we've spent centuries perfecting better and better clocks. And with each improvement in clock technology, we get a better understanding of the laws in physics, which we then formulate in a time irreversible way. But the very fact that we need to engineer clocks in the face of uncertainty and error in order to extract more information about the universe tells us in a way that manifest time is entering right in the very core of our formulation of the physical world, in terms of the way it's traditionally formulated, in terms of initial conditions and laws of physics, which tell you what evolves in time.
Great. The next question comes from Sayani Ghosh. I hope I'm pronouncing this correctly. From the process of post-selecting, where we see that if we start from an ordered count, n equals 1, there's a disorder as we trace to the past. Does this in any way violate the hypothesis which says increasing entropy / disorder is only in the direction of the future? In that case, is entropy a good measure to infer the arrow of time?
There's no doubt that entropy is increasing into the future, even for the kinds of clocks I have described. And that defines the arrow of time. It points to the future. It points to the fact that these counts, 1, 2, 3, 4, 5, are monotonically increasing into the future. And even though they fluctuate, they increase into the future, and the fluctuations as the count increases tells us what the arrow of time is. This post-selection of selecting only those past histories of the universe that happen to coincide with a particular reading defined by some local agent is a different aspect of the problem. It just tells you that the further back you go, the more and more possible histories of the world there would be that happen to coincide with a count of n equals 1 at a particular point in the experience of a local perspective. So I don't think this contradicts our notion that, in fact, it reinforces it, if anything, that entropy increases into the future. But if you post-select on a local event, it must also increase into the past from this perspective.
So this question comes from Robert Teague, which is the cosmos eternal?
Okay, now this is subject to great speculation. Of course, there was a big argument in the middle of the last century, which I'm sure Paul is better qualified to speak on than me, between the steady state universe and the Big Bang. In the steady state universe, the universe is internal. It just keeps creating stuff as it goes. And there's a wonderful novel in which this argument plays out, Fred Hoyle's novel, The Black Cloud. Our current view, if Big Bang cosmology is correct, is that the universe is not eternal, but was created in the Big Bang, as was time itself. But, you know, there are other perspectives. There's the possibility that the universe will undergo a big crunch and begin to contract, and everything will bounce over and over again at every Big Bang. But in some sense, that's just like resetting the post-selection point for the future of the particular universe that comes out of the big crunch. So in each universe, the universe will appear to have entropy increasing into the future because at the big crunch, as I said, almost by definition, everything was at the same place at the same time. Everything was coincident. So it doesn't really tell us whether the universe is eternal or not. For that, we're going to have to need more detailed physics and more astrophysical observations.
Great. So there's a few comments from Jeremy Boyd and a question. So he mentions it was a very good talk and didn't realize that temperature and time were related. So I think like those features. And then wants to know whether distance what's the role of distance in this whole picture of time?
That is a very good point. So, you know, in physics, time and energy are sort of dual to each other, and that's in fact ultimately why time and temperature are dual to each other. But there's also a duality between momentum and distance in physics. So in special relativity, this is represented by the fact that the generator of translations in space are momentum components, and the generators of translation in time energy components of the stress energy tensor. I'd like to think about that a little bit more to understand if there are thermodynamic constraints on the measurement of distance. There probably are, but I haven't really thought about it hard enough. But it does raise a very interesting question for further investigation, whether there are thermodynamic constraints on the ability to measure displacements as well as time.
Great. The next question is from James Garcia. If the expansion of the universe could be stopped and reversed, would time be reversed, or would time continue in another universe?
Interesting question. In the models I've looked at, we can set up learning models in which an agent is interacting with the universe and basically learning by looking at correlations between actions and sensations. When I reverse the time in those models, nothing changes, except for the fact that actions now become sensations, and sensations become actions, and things tend to propagate in from the future rather than out to the future. But the correlations between sensations and actions always stay the same. So the local agent will not know that global time has been reversed. They will still see the same correlations between what they are now calling actions and what they're now calling sensations. And this is a curious feature of these perspectival models. And I would like to spend a lot more time thinking about that. Now, there is other interesting speculation that maybe somewhere in the universe, time is flowing in the other direction. How would we ever know? Could we even communicate with an agent in such a universe? And these are really difficult questions to ask. I think Norbert Wiener asked this sort of questions back in the 50s. He was one of the pioneers of cybernetics, one of the early manifestations of computing, I suppose, and control. And he simply tried to explain that we could never communicate with an agent that was in a part of the universe where the arrow of time flowed the other way. But from the point of view of a local agent, reversing the global arrow of time doesn't seem to have any effect on how they learn. It's puzzling.
That's very neat. So Jack Drewson asks, if there's a perspective that we cannot escape, does thermal time exist in the absence of something that measures the counts?
Right. This is a good question, because I was always talking about local systems driven away from thermodynamic equilibrium. And the fact that I'm talking about a local system means that I'm talking about an open system. That's with energy and particle fluxes moving into it and energy and particle fluxes moving out of it. Now, if you take the universe as a whole, clearly it's closed by definition. It just is. So in some sense, neither space nor time exist for the universe as a whole. It just simply is. But from the point of view of any local agent, and time for us is always local, there does appear to be a thermal time.
Okay, the next question comes from Paul O'Brien, which is Bekenstein-Hawking entropy does not include the thermal degrees of freedom at the observable horizon. So how can it measure entropy, which must include temperature?
Okay, this is quite a good technical question. Again, but here, we know from Hawking's work and Bekenstein and others, Unruh, that a black hole is a thermodynamic object, and it radiates as if it was at a particular temperature. What we don't know how to do is to calculate from some microscopic quantum theory what those degrees of freedom are that we're coarse graining over to refer to temperature. Indeed, the fact that a black hole emits thermal radiation suggests you could make a thermal clock out of it just by putting a little atom close to it. Would be a pretty slow clock, because the temperature of Hawking radiation is pretty low. But that's all that would remain of time near the horizon of a black hole, is the thermal radiation coming out. I know Paul has mentioned something called the Unruh-Stravinsky effect, where a rotating black hole does produce something like a limit cycle on the radiation that's emitted. It gets these pulses coming out, and that would also make a very good clock. I haven't looked at the thermodynamics of that, but it's something that one should really look at. So I think the Bekenstein-Hawking argument tells us something very important about the nature of time and quantum physics that we just can't answer at the moment. The nature of time and its relationship to temperature, and we just can't answer clearly at the moment without a microscopic theory of gravity, which would necessarily involve quantum physics. As we don't have a quantum theory of gravity, or at least none that's convincingly enough developed to establish general relativity in the semi-classical limit.
Great. An anonymous participant asks, can you say anything about time and the idea of so-called retrocausality?
So this is actually where I entered the debate on time and causality. And it was discussions with an Australian philosopher who at the time was in Cambridge, Hugh Price, who has argued cogently, and to some extent it hasn't been fully answered yet, that some of the puzzles in quantum physics, like the violation of the Bell inequalities, are an indication of retrocausality, in the sense that future events are influencing local events here and now. It's a little bit hard to go into, but the reason it conflicts with our standard notion of causality, as I've hinted at, causality is an agent perspectival concept. It depends on intervening in the world and watching how the world reacts. Now, it's not inconceivable that interventions in the future couldn't change events in the past. It's just putting aside Hugh Price's conjecture, we have no evidence for that. But from my perspective, in the absence of any sort of quantum way of accounting for space-time, it seems to me retrocausality is unlikely from the point of view of an agent. Now, from a global perspective, maybe we will eventually have to introduce something like that. Now, there is one example where it could happen, and that is in the Bell inequality. Typically Einstein-Podolsky-Rosen puzzles where two entangled particles spin up, spin down, go to opposite parts of the universe. If one side measures spin down, the other side measures spin up. Because they can't communicate with that protocol, that's just a correlation. But you could imagine a situation where they were allowed to come back to the local agent that generated the entanglement, and one came back before the other. So the earlier one coming back will be spin down. That means you're guaranteed to see the later one spin up. But you could have just as easily said, well, because I saw the later one spin up, I saw the earlier one spin down. And that is a kind of local retrocausality, although I'd caution that correlation is not causality. The intervention that actually took place was much earlier, and that was the creation of the entangled particles in the first place. Everything else followed from that.
Yeah. The next question is from Sarah Chahid, which is, what is the correlation between time and the gravitational force, and how is this time manifest in the absence of the gravitational force?
Okay, so in general relativity, the nature of space and time are determined by matter and energy, and it's the energy density that essentially determines the local flow of time, and that appears to us in the weak energy limit as a sense of Newtonian time and the sense of Newtonian gravitational interactions. So the appearance of time in general relativity is tied to the local structure, the local density of mass and energy. And likewise, of course, gravitational field influences the future evolution of mass and energy densities. So they are tied together in the general theory of relativity. Not so much, well, certainly not at all in Newton's theory. Time is just postulated as absolute and always flowing and so on. It's just a static background that's not influenced by anything you do. It's sort of an arena in which things take place. But in general relativity, it's much more relational. It's a question of relating one event to another event in some local region of space and time.
So we have a question from Tibor Molnar. Anything that participates in the dynamics of the universe acts in at least some sense as a detector. Does a detector have access only to manifest time? And if so, what is the role of thermal time? Is thermal time an abstract mathematical construct?
Okay, so let me address the question of detector. So this typically turns up in quantum physics as the thing that makes the world real to us. So in quantum physics, there's this notorious problem of the measurement, and that is nothing seems to be a fact of the matter until you make a measurement. And a measurement is made by a detector, which is some physical system at some particular point in space. The measurement events have some randomness due to the underlying quantum physics, but they are irreversible. They are necessarily irreversible, and they are open systems driven from thermal equilibrium because they typically have to be initialized in some way. So, for example, an atom prepared in the ground state. When it detects a photon, goes to the excited state, and then something else ensues, some photocurrents are generated, which make it completely irreversible. Hang on, I'll just close this door. So all detectors in quantum physics are necessarily irreversible devices, and therefore any detector which is based on a time series, a timestamp, will be subject to the irreversibility and the fluctuations that I described. So all detectors have access to manifest time in a sense, although they're not learning devices, so they don't, know anything. We look at them. We're the ultimate learning device that looks at the detector, and we have access to manifest time. Now, the next question part of that was, what is the role of thermal time? Okay, so any detector is necessarily subject to thermal noise. We can sometimes do our best to make them very, very cold, because in the case of a two-level, some photodetector, you don't want it just to click just due to some random thermal fluctuation passing by. You want it to respond to the actual signal you're trying to measure. Likewise, if you have a little needle, you don't want it to be just sort of wobbling around due to random Brownian motion too much. So you would cool it down or increase the friction or do something which necessarily limits the signal. So any real detector is subject to thermal noise, and there's nothing you can do about that, because a detector is an irreversible system, and by definition of the fluctuation dissipation theorem, it's subject to noise. So it's not a mathematical construct, although we do have good mathematical theories of how these devices behave, but it's experiment. The fluctuation dissipation theorem comes from experiment. It guarantees that systems can reach thermodynamic equilibrium.
Great. There's a question from Stephen Sickle. Would it follow that we're limited in our study of time by our perception of it, or does our instrument reconcile this? Granted, we perceive these devices from the same everyday perception. So I think this is exactly what you were just saying. But
it is to some extent. So
Yeah.
what's important here is this notion of, do agents share the same view of the world? So even though an agent such as ourselves may have clocks in our heads that are helping us learn and coordinate coincidences, each one will be different for each person, and each clock is different. But nonetheless, we're all built from the same stuff, more or less. We all have very different experiences. We've all learned different things, but we all can agree pretty much on the coordination of local time. So I suppose in that sense, it comes back again to this notion of time being local and perspectival. But now, of course, there's a certain objectivity that arises when a community of local agents comes to some agreement on the coordination of coincidences in their local environment. That may be ultimately where we reconcile the subjectivity of manifest time and the objectivity of physics.
Great. So there's a question from Dennis Boyle, who had the first question also. And maybe we could infer this already from what you've said, but let's see what your official stance is on it. Some argue that the present moment, the now, is an illusion because physical theory does not acknowledge it. Do you disagree?
Yes, I do, because physical theory does acknowledge it. If you take this point of view, that what matters to me now is all the things that are coincident and coming into me from this perspective. Okay, in the future, they're going to become disordered, and all those events in the past that led to now have been disordered. So this notion of illusion, I think, comes from something Einstein said in response, I think in response to the death of a close friend of his. It comes from the notion of a block universe, that, space and time just exist as a block. The now is just an illusion somehow or other. But what he's hitting at is not an illusion. It's just, the fact that it's a perspectival thing. It depends on who is observing the universe in the local environment, or what is observing the universe. It doesn't have to be a human. You could build machines that could function just as well as us in learning about the local environment. In fact, we do. That's what a robot is meant to be. So no, I disagree. Now is not an illusion.
Excellent. We like disagreements in the Beyond Center, so that's good. The more provocative, the better, as long as it's grounded in reason. Okay, this one's going back to the question of consciousness. We maybe only have enough time for one or two more questions. This comes from Derek Youngson. If conscious human beings experience time due to the brain processing a series of images that flow, can non-visual creatures or inanimate objects experience time? So this goes back to something that you were mentioning earlier, but maybe can elaborate a bit more.
Oh, yeah, absolutely. In fact, one could imagine places in the universe where there are, if not conscious, at least sentient beings, learning machines, that don't need images at all. On Earth, there are animals, bats, that don't rely on vision, they rely on sound. There may be places in the universe where they rely on sort of tactile vibrations coming through some solid material. There are many ways in which you could build a learning machine with different kinds of sensors and different kinds of actuators that have nothing whatsoever to do with visual images, but they all must be dissipative, and they will all necessarily perceive the world in terms of manifest time.
So an anonymous attendee asks, what defines the arrow of time?
As I said before, it's this notion that disorder increases into the future. And so even if we pre-select all those clocks that happen to read the same count right now, so piano sounds, and we look at all the clocks, and we only keep those that read n=1, we throw the rest away. Now, as the piano continues on changing, those clocks will begin to get out of sync with each other due to the noise. And that's an indication that entropy is increasing into the future.
Great. Since we only have a few minutes left, I'm going to end on kind of a more lighthearted, fun question. But can you think of any everyday products or activities that might be improved as clocks become more and more accurate? So what are the implications of what you're doing for the future of all of us?
Oh, well, the business of making very good clocks is a big business indeed, for many reasons. We've already addressed the one in quantum computing. So the problem is we do have good clocks. They're atomic clocks. They're sitting in the lab in various standards laboratories around the world, but that's not much good in a quantum computer. It has to be in the computer. It has to be right next to the physical devices that are doing the computing. And in many devices, like at IBM and Google, these are superconducting devices in a fridge. And so we need really good clocks at really low temperatures sitting right down there next to the quantum computer. And so the sorts of things we're discussing on the thermodynamic limits to clocks will be extremely important for that technology. Even at current atomic clocks, the ultimate reason why atomic clocks are so good is because the laser, which is driving them, functions on a limit cycle. And the harder you drive it above threshold, the better the clock it is. Of course, it's hard to count ticks and tocks at optical frequencies. So much of the technology is based on dividing it down to something we can count. So making devices, nonlinear devices, open nonlinear devices that have better phase performance than a laser is certainly an important part of future clock design. But in terms of how it affects our everyday life, well, I guess that's a question of how quantum computers will affect our everyday life. And while there's been much speculation on that, it's a little bit hard to say at the moment because they're not part of everyday life just yet.
Right. So I'm going to take my liberties as a moderator to ask you the final question, which is actually just a more general sort of advice type question. But do you have any advice for the young people in our audience who might want to work on fundamental problems like this, how they might approach it? Because you're very brave in the kind of questions you ask and the ways you think about it. So I think that
yes, well, as you can see, got a gray beard, so it's a little bit easier for me to ask questions that can't be answered, I suppose. I think the important thing is to be in contact with experiment. Go and look at what clocks actually do in the lab and ask, what do you do to make that clock good? What do you mean when you say, a certain event happens every femtosecond? And so focus on what is actually happening in the lab before you start generalizing and theorizing too far. That would be my advice.
Excellent advice. I think that's about as good as we can hope for as far as critical thinking while working on the edge. Fantastic. So I want to thank you again so much. This was really lovely. I've already had requests for the recording. I think people want to go back through and kind of get the volume of information that you've shared with us this evening.
Sure.
And many thank yous from people's questions that you answered. And I also want to thank our audience for joining. I think this was truly an international event with friends from Australia and people from all over the world joining. So we're grateful for all of you joining us and asking such wonderful questions. And we look forward to these events in the new year, and stay tuned for our upcoming series of Ask a Physicist with lots more provocative topics coming up. So thank you again, Gerard. That was fantastic.
You're
And
welcome.